We already discussed in one of the previous lectures how to build a duplexing network using directional couplers. For example, what is shown here, we have two users, one on the left and one on the right, and they can communicate both ways by utilizing two directional couplers. The signal from user 1 could be transmitted to user 2, and the signal from user 2 could be transmitted to user 4. But effectively, if we look closely on how many ports of each of the directional coupler we utilize, it is actually 3, not 4. And the directional coupler is capable of providing 4 ports. So we might get away with a simpler version of a coupler, not with 4 ports, but with 3 ports. And an example of 3-port coupler is shown on the next slide. Here we have the same functionality of a full duplex network between two users, but the couplers are not 4-port directional couplers, they are 3-port couplers. And what is shown here is a schematic view. Those 3-port couplers are often called Y branches. Y meaning that you see there are legs, so it stands for, describes nicely 3-port coupler, so normally it's called Y branch. And we go to next slide to see it in more details. Y couplers, also called Y branch power splitters, are constructed utilizing integrated optics technology, also called planar waveguide technology, by constructing waveguide patterns inside the substrate. And here is an example of Y branch splitter or coupler. So we have incoming light that is split from one waveguide, split between two waveguides, and the light is split 50-50. This is essentially a 3 dB coupler. Integrated optic directional coupler is built inside or on a substrate by constructing waveguides. And here is 3 views, right? So of a substrate, this is a view from the top, is from the side, and this is from the other side. And effectively, the cross section, it could be either rectangular or circular. We are not going to discuss here in more details integrated optics, also called planar waveguide technology. We will discuss it in a bit more details in the next module. In fact, Y couplers are very difficult to build by using other technologies, for example, fiber technology, but it is very easy to build using integrated optics or planar waveguide technology. And here what we see one more time is stem and then two arms where light is split from port 1 between port 2 and 3. What is interesting here that in the direction when we start from the left and see how much light we will have in port 2, it will be 50%. So our losses will be 3 dB. But what if we couple light from port 2 to propagate to the left? How much light will enter to port 1? First of all, nothing from port 1 will be coupled to port 3, but only 50% of light will continue to port 1 and 50% will be just lost. It is perhaps surprising and not very intuitive to see, but it's really how it works. No matter where we start, which direction light propagates, you will have loss 50% anyway in each of them. What you can see here is my handwriting, and I was just trying to make a schematic to explain why, for example, when we couple light from fiber 2 to fiber 1, we lose 50%. So assume that we are going to build a Y coupler. So we have a stem one fiber, and then light is split to fiber 2 and then to fiber 3. And the size of the fiber is the same. Therefore, you see that part of fiber 3 will extend beyond fiber 1, as well as part of fiber 2. Now, as for the light, so light 50% will continue when we start from the left, from fiber 1 and follow this red arrow. 50% will continue to fiber 2 and 50% will continue to fiber 3. Now, when we go in the opposite direction, for example, let's follow this blue arrow starting in fiber 2. When it reaches fiber 1, 50% will go inside the fiber and 50% will be just lost. And the same happens when we launch light to fiber 3, green arrow. Also, when once light is coming here at interface between fiber 3 and fiber 1, 50% just go outside the fiber and are lost, and only 50% will continue through. It's just schematic, it's not a realistic schematic, but it gives some sort of physical understanding what's going on inside Y branch, even built not by using fiber technology, but planar waveguide technology. Still, no matter from which side we start the light, we will still suffer 3 dB losses. Y branch, Y coupler is good enough by itself to build 3-port devices, but if we need extension to more ports, we can actually connect Y couplers together, forming a tree. For example, what is shown here is 1/8 coupler or 1/8 splitter built by using Y branches. So you see, we start with one Y branch, and then here it's second Y branch, and then 2 more Y branches. So total in that system we have 1, and then 2, and then 4. So we utilize here the constructed 1/8 coupler by using 7 Y branches. But functionality of this device is not 1/3 or 1/2, right? It was in the case of Y branch. Y branch is actually 1/2. It has 1 input and 2 outputs. And here, by using several Y branches, we can build a different functionality. And different, of course, could be arranged. 1/8 is one of the examples. So you see, Y branches are useful devices by themselves, and they can be used to build a more complex couplers. That is all for this lecture.